Statistics is concerned with making inferences about a population. We do that by conducting statistical experiments. The statistical experiment is any process that we go through that generates a set of chance outcomes. Now, before, when we were talking about sample spaces, we were talking about making a list of all of the possible outcomes when we conducted a statistical experiment. Now, sometimes it's really helpful to us to take a look at our sample space and to assign numbers to the elements in our sample space. When we do that, we're using a thing called a random variable. A random variable is a function that assigns a value, a real number value, to every element in our sample space. Now, take for example, I'm tossing a coin 3 times. And when I toss that coin, I really am only concerned with how many times does heads appear. So heads could appear 0 times, 1 time, 2 times, or 3 times. And how many times it appears, that's the value that I'm going to assign by use of a random variable to each of my elements in my sample space. Sometimes when we're assigning values to the elements in our sample space, we're concerned with more or less the answer to a yes or no question. An example of this is the product defective or not? So I take a shipment and I'm going to take a sample of 8 products from my shipment, and I'm just checking, is it defective or not? I'm going to give it a value of 1 if it is defective and 0 if it's not. Now, when we do that, when we assign a value of just 0 or 1 to an element in a sample space, and we do that for every element in the sample space, then what we've done is we've assigned a Bernoulli random variable. Now, random variables can either be continuous or discrete, and we can tell which one it's going to be based on looking at the sample space. If a sample space has a finite number of elements in it, or it has a countably infinite, so think about being able to sit and count the elements in the sample space, and you could actually count them all if you had enough time in some kind of linear fashion, then it's called a discrete sample space. And the random variable that we use to assign values to that sample space is called a discrete random variable. Now, on the other hand, sometimes random variables are continuous, and we also tell that by looking at the sample space. So, if the sample space has so many elements in it that you couldn't possibly count them all in some kind of linear fashion, you think about trying to count how many points there are on a line segment, and like there's always a point between 2 other points, and then you count that one, and then there's a point between that one and another one, and you just can't count them all because it just spirals out of control. It's uncountably infinite. Then you have a continuous sample space, and the random variable that assigns values to the elements in that sample space is called a continuous random variable. We're going to talk about discrete random variables first. Now, discrete random variables assume that there's some probability assigned to each of the values that the variable may take. A simple example of this is a random variable that can take the value of 1, 2, 3, 4, 5, or 6, simulated by rolling a die. And the probability that's assigned to each of the outcomes is 1/6. Venturing into probability with our discrete random variable, we can make probability distributions, cumulative probability distributions, and probability histograms. Probability distributions are also known as probability mass functions and probability functions. All of these represent the same thing. For each of them, they're a set of ordered pairs, x, f of x, where f of x is going to be greater than or equal to 0 for all of the x values. The sum over all of the x values of f of x is going to equal 1, and the probability that our random variable has the value of lowercase x is f of x. So what these really are is ordered pairs of the value of the discrete random variable as the first part of our ordered pair, and the probability of that value as the second element in our ordered pair. So whenever we're asked to check if something is a probability function, probability mass function, probability distribution, what we really need to check are these three things: that the ordered pairs are the value of the discrete random variable and the probability of that value, that the sum of all of the probabilities equals 1, and that each probability is greater than or equal to 0. Now, when we talk about the cumulative distribution function of a discrete random variable, what we're doing is we're taking and we're adding together all of the probabilities that the random variable takes on a value less than some value x. And that's the value that we assign to our function f of x. Let's consider a simple example of rolling a die. So when we roll the die, it can have outcomes of 1, 2, 3, 4, 5, or 6. Those are all possible x values for my random variable. Now, if I consider f of x in my probability distribution, what this is the probability of each of those numbers occurring. So the probability that I roll a 1 is 1/6. The probability I roll a 2 is 1/6. A 3 is 1/6. A 4 is 1/6. A 5 is 1/6. And a 6 is 1/6. So this right here is my probability distribution. And I could write it out as the ordered pairs 1 1/6, 2 1/6, 3 1/6, 4 1/6, 5 1/6, and 6 1/6. And that would be another way of representing my probability function. Now, if I want my cumulative distribution function, now when I'm looking at the cumulative distribution function for discrete random variables, I end up with a piecewise function that's actually going to have one more piece than I have possible values for my random variable. The first piece is always going to be for the value of my random variable being less than the smallest value that it takes on. Then I'll take values of my random variable that are greater than or equal to the smallest value and strictly less than the second smallest value. And I'll progress this way until I've reached the top value. So I have 3 less than or equal to x less than 4. 4 less than or equal to x less than 5. 5 less than or equal to x less than 6. Then I have my final entry where x is greater than or equal to the largest value it takes on. For the first entry, since my random variable can't take on a value less than the smallest value it takes on, then the probability is 0 that that happens. Then moving along, the probability that my random variable takes on a value between 1 and 2, with 1 included, well, my random variable can have a value of 1, and that has a probability of 1/6. That's the only way that it's between the two. So I have a value of 1/6 there. Now, the same thing happens between 2 and 3 with 2 included but 3 not. The probability that my random variable is in that window is 1/6. But we're dealing with a cumulative distribution function, so what it's going to do is it's going to add together the probability that I'm in this window plus the probability that I'm in the last window. So I'd have a value of 1/6 for this window plus my 1/6 from above. So I would have a total of 1/3. And now I move on to the next window, and again, the probability that I'm in the window of 3 to 4 with 3 included and 4 not is 1/6. But since I'm dealing in a cumulative probability function, I'm going to add the value above. So I'll add the 1/3, and I'll have a total cumulative probability of 1/2 when my random variable is between 3 and 4. And then moving on to the next step, again, that I'm between 4 and 5 with 4 included, 5 not included is 1/6 plus the 1/2 that I had above. So I have a total probability, cumulative probability of 2/3 in the 4 to 5 window. And then between 5 and 6, 5 included, 6 not, I have 1/6 plus 2/3 from above. So I have 5/6 as my cumulative probability in my 5 to 6 window. And finally, x greater than 6, including 6, is 1/6 as well. And I'll be adding to that the 5/6, which gives me a total cumulative probability of 1. So one of the things that we like to do with these is plot them so that we can see on a graph what's happening. So on my first, I have a value of 1, 2, 3, 4, 5, and 6. And the probability is somewhere between 0 and 1. And we're specifically going to care about 1/6 because that's where everything falls for my probability distribution. So here's my probability distribution as a graph. So I have 1/6 as the probability of getting 1, 1/6 as the probability of getting 2, 1/6 as the probability of getting 3, 1/6 as the probability of getting 4, 1/6 as the probability of getting 5, and 1/6 as the probability of getting 6. Other times, what we actually want is the histogram. So to turn a probability mass function plot into the histogram option, all we do is we make bars that have the max height of the probability where they're centered at the value that the random variable takes on. So this one's very easy to make because it's the same value straight across. But that is our probability histogram. Now it's also sometimes helpful to graph the cumulative distribution function. So with this one again, my horizontal axis will be labeled with the possible values for my random variable. So I have 1, 2, 3, 4, 5, and 6. And then I'll have my y values. I know that my probability has to be between 0 and 1. And I know that I'm going to end up with cumulative probabilities between 0 and 1 in increments of 1/6. So when I plot my cumulative distribution function, I know that if x is less than 1, so everything right up to 1 but not including 1, so I use an open circle at 1, then my value is 0. And now I know between 1 and 2, my cumulative distribution, 1 is included, so I put a closed circle there and an open circle at 2 because it's not. But any x value, any value for my random variable between 1 and 2 is going to have a cumulative probability of 1/6. And then I do the same thing between 2 and 3, bumping up to 1/3 as my y value. The same thing between 3 and 4, bumping up to 1/2 as my y value. Bumping up to 2/3, same thing between 4 and 5. And bumping up to 5/6, same thing between 5 and 6. And then finally I get to, at 6, a value of 1, and that continues on forever. So whenever I plot a discrete cumulative distribution function, it's going to look like a step function.